In this video, we're going to learn about right triangles, a topic called trigonometry. And we're going to use this in physics to add vector quantities, quantities that have a magnitude and a direction, where the direction is often specified by an angle. If you haven't seen this before, here's a quick rundown. This is a picture of a right triangle. I've labeled a lot of different elements of it and different terminology. What makes it a right triangle is this 90-degree angle. All triangles, the angles within a triangle always add up to 180 degrees. And if this is 90, then these other two angles have to add up to 90. Right? 90 and 90 is 180. We call these complementary angles. The common physics labels for these angles, the first one we typically use is one called theta. It's a Greek letter theta. It looks like a circle with a line through it. And then another angle, if we've used theta up, we might go to alpha as another angle measurement. You might go to beta as another angle measurement. But in this class, you're going to pretty much use theta almost exclusively. So let's look at this triangle. If we got alpha, we got theta. What are these sides of the triangle called? Well, every right triangle has two legs. These are the shorter sides that connect to the 90 degree. And then the longest side is always called the hypotenuse, and it's across from that 90 degree angle. And you'll sometimes see it labeled A, B, and C as the two legs are A and B. The hypotenuse is C. And that leads us to this first right triangle theorem called the Pythagorean theorem. And what that says is that if you know the length of A and B, that if you square A, you add B squared, that's going to equal C squared. And with Pythagorean theorem, if I know any two side lengths of a triangle, I can always find the third, just with a little bit of algebra. So I can solve for A, B, or C in that equation if I have the other two. Now, what we're going to deal with is a situation where I only have one side and one angle. And this is where you need to learn about some trig functions. So let's look at these functions right here. These are the basic trig functions: sine, cosine, and tangent. And you're going to remember a mnemonic, a way to remember these three equations for these trig functions. SOHCAHTOA. So you're going to hear SOHCAHTOA. And that's SOHCAHTOA. And SOH says that the sine of the angle is equal to the opposite side over the hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Right? And with these equations, if I have an angle and one of the sides, I can find the third by solving for it in this equation. Well, what is an opposite, an adjacent, and a hypotenuse? Well, we already learned about the hypotenuse here. It's the longest side. Well, the opposite or adjacent is going to be one of the legs, and it depends on what angle you have. If I have theta as the angle given, the opposite leg is therefore going to be A. It's the one across from theta. Right? It's opposite to theta. The adjacent leg will therefore be B. B is the adjacent. It is next to, which is what adjacent means. However, if the angle I have is alpha, well, now B is the opposite leg and A is the adjacent. So these legs can be opposite or adjacent depending on what angle you're given. Right? So let's come down here and let's talk about these angles. Right? So all we need to understand is these trig functions really tell you about ratios of side lengths. Right? Depending on this angle, this side length is going to be compared to the hypotenuse or compared to B in a specific way. And there's some angles you're going to learn as you get into trig that are common angles like 30 or 60 degrees where you see a relationship here. We're going to look at one in particular here. So let's look at how we might use a trig function or what they equate to. So the sine of 30 is a ratio, right? And it is a ratio of the opposite leg over the hypotenuse. And it turns out that ratio is exactly 1/2. If I have a triangle right here with a 30-degree angle right here, the opposite leg, in this case, is 5. Well, then the hypotenuse would have to be 10, right, at 30 degrees. And it doesn't matter how big the triangle gets, as long as that angle remains constant, if I stretch it out to this red one, and I double this opposite leg to 10, well, now the hypotenuse is 20. The ratio, the sine of 30, will always be this opposite over the hypotenuse, and at that particular angle, it is always 1/2. right? So let's pull out our calculator. I'll show you where these trig functions are located, right? We have the sine, the cosine, and tangent functions right here prominently in the middle of your calculator, right? So let's take the sine of 1/2, or sine of 30 rather. So we always put the sine and then the angle measurement inside, right? You could put close it, the parentheses, or not. And when I hit enter, I should get 1/2. I got negative 0.988. But we just saw we should get a ratio of 1/2. Well, what's going on here? Well, many times your calculator will not be in the right mode. So as we have here, we talk about angles. Angles can actually be measured multiple ways, in radians or in degrees. The most common way we think of them is degrees, but you'll learn about this other measurement called a radian. And they both measure the degrees, but in different units. So if I'm looking here, I've got a different degree measure. I got 90 degrees in black, 180 in green. If I go all the way around, I'm at 360 degrees, right? The number all the way around a circle. Well, it turns out 360 degrees is the same as going 2 pi radians, or about 6.28 radians if I multiply 2 times pi. Going halfway around 180 degrees is the same as pi radians, right? And so radians is just another way to measure angles. And your calculator and Microsoft Excel, most computer programs like working in radians. So if I go into mode in my calculator, you'll see that I can change scientific notation, I can change the number of decimal places, and right here, radian or degree. We need to be in degree mode in our calculator in this class. If we're going to be in here in this class, we're going to make sure we're in degree mode anytime we're using these trig functions. So if you're not there, do that now. Switch your calculator to degree mode. Later in the year, your math class might go to radians. You might have to remember to switch back. And now when I put in the same exact thing, the sine of 30 now is 1/2. All right, so this is how we want to run it here. All right, so we now have our calculator in the right mode. Let's look at how we're actually going to use this. So in this unit, when we're first learning about trig, we're going to be using our trig to find the pieces of velocity vectors, right? Remember, a vector is just some quantity with magnitude and direction, and velocity has a direction. In this case, we have a velocity of 10 meters per second at an angle of 30 degrees. Now, when we solve projectile motion problems, remember, we want to look at how it's going in the horizontal direction, the x, and what's happening in the y. However, this 10 meters per second is kind of in both, but it's not all 10 in the x and all 10 in the y. It's only some of it. Well, and this is where these trig functions come into play. If I do the projection of this downward, I see that this blue arrow drops right underneath it. That would be how much of it is in the x direction. And this red arrow is how much is in the y. And if I move this arrow right over here, this little dotted line, we start to see that, hey, I've got this triangle here. And if the length of an arrow represents how much I have, if that length is 10, well then this length of the blue one should be how much velocity we have in the x, and the red length should be how much is in the y, right? And so if I'm starting a problem, I want to know, well, how much velocity did I have in the x and the y to put in my ATVX table? I'm going to do some trig with 10 and 30 degrees. So if I want to know how much is in the y, which is going to make the object go upwards, I know that this is the opposite side to 30. I have the hypotenuse, so I want a trig function with O and H, and that's what sine is. SOHCAHTOA, S-O-H, sine of the angle is equal to the opposite side, I don't know Vy, over the hypotenuse, which is 10. And in algebra, I would multiply both sides by 10, and I'd find that Vy is equal to 10 times the sine of 30 degrees, and in your calculation, you get it that it's 5 meters per second. Right? The length of that arrow is 5, and that is a velocity vector arrow, so I would label it with meters per second. Now, the blue one is the adjacent side. It is next to 30, so you would use cosine. The cosine of 30 is the x piece over 10, and I get 8.66 as the velocity. And it turns out, if I actually wanted to use this angle up here, I know if that's 30, that's 60. Well, then the x piece, I would use the sine of 60, and I would get Vx, and lo and behold, the sine of 60 times 10 is also 8.66. So I can actually use any of these angles, but I'm going to stick with the one typically given. So now what happens if I drop that angle lower? If I drop it to 20 degrees, less velocity is up, more is horizontal. And sure enough, I see that the y piece got lower, right? And the x piece got longer. If I drop it a little more to 10 degrees, more of the velocity is horizontal. And now I have almost all of it, 9.85, and just a little in the y. Right? So we see these pieces of the velocity vector in each direction, and we can figure them out with trig. Notice they don't add directly to 10. They technically do if we're adding them as vectors, but as numbers they don't. And if we drop it a little lower at 5 degrees, almost all of it is in the x, just a little bit in the y. And if you go all the way down to no angle, well, you get no opposite side, and therefore no y velocity. In this case, all the velocity is in the x, and we would just say it's fired horizontally, a 0-degree launch angle, right? And so we wouldn't have to do any trig at all. All the velocity would be in the x, and none would be in the y. And we've seen some types of problems like that with trig, or with projectiles. Now, sometimes the angle is actually really big. At 80 degrees, right, you get almost all of it in the y. And at 90 degrees, the sine of 90, right, is actually 1. And so I get all of the velocity in the y direction at 90 degrees, where I'm firing it straight up and down. Right, so these are some trig identities that you'll recognize. That sine of 0 is the same as cosine of 90 at 0. Sine of 90 and cosine of 0 is 1. Your calculator will spit that out, and you're good to go. Now, the last thing I want to touch on is what happens when you have two sides but no angles. And this is where we can still use a trig function, but we're going to use the inverse trig functions. And I'll show you how that works. In this case, I don't know theta, but I know the opposite and the adjacent. Well, which trig function has opposite and adjacent? That is TOA, tangent. And so I know that this equation is true. The tangent of that angle would be the ratio of 4/7, the opposite over the adjacent. And so I have an equation now, and actually have a variable tangent. How would I solve for tangent, or for theta? Well, I would effectively divide by tan. And that's kind of what taking the inverse is. And that's kind of how I would describe these inverse functions. So if I ever want to know an angle, I can still use SOHCAHTOA, right? Sine, cosine, tangent. But I'm going to be using an inverse trig function because I'm finding an angle. And it turns out the inverse trig tan of 4/7 is that angle of 29.7 degrees. In my calculator, to do the inverse trig functions, above each is the inverse. So I would go second tan. The ratio is 4/7. And I would get 29.74 degrees as that angle. All right, so again, here are the inverse trig functions. If sine of theta is opposite over adjacent, then theta is the inverse sine of the legs, the opposite leg and the hypotenuse leg. So a quick crash course of all this trig functions. If you remember SOHCAHTOA, you remember to be in degree mode, and you just remember to write out the actual equation, and you can identify those legs, then they just become simple algebra. If you're not familiar, it does take some practice, but with a little bit of practice, I think you'll find you can have some success. Fortunately, as we get into projectiles, you're going to see a setup like this with an angled velocity vector, and you're going to be finding the x and y pieces. And you'll find that the steps you take for the trig tend to be the same steps over and over again. It's not until we start adding vectors later in this unit where we might see the trig change a little bit. But the same basic rules come into play, and you can refer back to this video to cover any of the content moving forward.